F322 June 2012 question 3. This question is going to look at equilibria, catalysts, percentage yield, and then some extra stuff on atom economy. So we're starting off, we've got this equation here. We're making hydrogen in this case from methane and water, and we're producing carbon monoxide, which when you see carbon monoxide you immediately think of toxic gas, and hydrogen, which can be used to make margarine and ammonia. So we're going to be asked about equilibrium here. The pressure of the equilibrium mixture is increased. Explain what happens to the position of equilibrium. So with pressure, we're always looking at the number of moles on either side. So here we've got 2 moles on this side, and here, that was interesting, that'll be 4 moles on that side. So with an increase in pressure, Le Chatelier's principle states that if you impose a change on a dynamic equilibrium, the equilibrium will move to minimize that change. Here, the power of the system to minimize a change over pressure is to say, well, if I produce less molecules, that will lower the pressure because there's less molecules then to bash into each other. So if the mixture, the equilibrium mixture, the pressure is increased, the equilibrium to oppose that change, oh, that's interesting, I lost my cursor again, here it is, will move from the side with more moles to the side with less moles. So my equilibrium will shift to the left, to the side with the least number of moles. And I'll get my screen block out of the way now. So the answer to this one, I've got equilibrium shifts to the left as there are fewer moles on the left, or you could use the reverse argument. Importantly, in these equilibrium questions, if you make a mistake on the first part, they can't credit you for the second part. So you have to be very careful about which is your left and which is your right. The next question then, the temperature of the equilibrium mixture is increased. Key thing to look at here is this sign. Don't have to worry about this number at this point, it's this sign. We've got delta H is equal to plus 210 kilojoules per moles. So if it's 200, if it's plus, the reaction is endothermic, which means that in the forward direction, because this value is always for the forward direction, moving to the right, we've got that the reaction will absorb energy. It will take energy in for the reaction to occur if it's endothermic. So what will happen to the position of equilibrium if the temperature is increased? And we've got then that the equilibrium will shift towards the endothermic direction, so it will shift right to favour the endothermic reaction, and I've got that written in here hopefully. So the equilibrium shifts to the right to favour the forwards endothermic reaction, and that key bit that it's the endothermic reaction being favoured is very, very important. Again, if you don't get the direction of your first part right, you do not get the second part either. So part C, the reaction is actually carried out, and this is a very standard one, isn't it? They've got you to have a little bit of a way up of the equilibrium. Now they're saying in reality, the reaction is carried out with a nickel catalyst at a pressure of 30 atmospheres. So not a massively high pressure, but certainly higher than atmospheric pressure. So it's going to ask you then, suggest why the manufacturer uses that 30 atmospheres. And if you think about it, we've said that an increased pressure will shift the equilibrium to the left, which is where we don't really want it to be because we're trying to produce hydrogen. So there must be another reason that they're using this high pressure. And of course, If the equilibrium's not favoured, then think about, right, equilibrium mustn't be that, it must be rate. So if we think about the rate of reaction, if you increase the pressure, you increase the rate. So you get 1 mark for saying that you'll increase the rate, or it will give a reasonable weight without shifting the equilibrium too much to the left, so back to the reactant side, which is where you don't want to be. Then moving on over the page, then it wants to start looking at catalysts. So using and notice how it says a labelled diagram of Boltzmann distribution. So many people forget to put labels. On the y-axis, number of molecules. On the x-axis, energy. Notice how I'm going through the origin, so 0 molecules with 0 energy, and how I'm not touching the axis as I come down. I'm tapering off. It's very important that you don't touch the axis there. Then I've marked on an activation energy, and clearly an activation energy with a catalyst. So my first mark is for a labelled diagram as it's asked for. So it's nickel catalyst increases rate. Explain why the catalyst increases the rate. So we've got this diagram, we've got the diagram correct. What we're essentially saying is, with a catalyst, my activation energy is lowered. So it's moved back. I'm now at a lower energy here, since this is 0 energy and this is high energy here. I'm at a lower energy, which means then I've got this whole section of I've got a greater proportion of molecules now that have an energy. This area under the graph is proportional to the number of molecules, so I've now got a greater proportion of molecules with an energy higher than the activation energy, so therefore more successful collisions and a faster rate of reaction. So here we've got catalyst lowers the activation energy, which can be shown from your graph as well. More molecules have an energy above the activation energy, and so more successful collisions. So you always get 1 mark for drawing out that Boltzmann distribution and labelling the axes. Please label the axes. Then catalyst lowers the activation energy, and then it's talking about, if when you've got a Boltzmann distribution, always talk about that proportion of molecules here. So there's a greater proportion of molecules now there that have an energy greater than the activation energy. Part D then is a percentage yield question. You've got in this question 200 tons of methane being put into this factory, reacted with water, and you're producing an actual amount of 68.4 tons of hydrogen. So 68.4 tons actually coming out. So calculate the percentage yield of hydrogen. What I need to do then is get into this equation so I can use the ratios. So I must convert my 200 tons of CH4 into a number of moles. So I'm timesing by 10 to the 6, though I wouldn't really need to do that because it will just cancel out as I go through. So number of moles is 200 divided by the MR of methane, which is 16, and I get 1.25 times 10 to the minus 7. I'm not going to try and say that number. Then I know the number of moles then here, so I can take my ratio to here. Notice it's a ratio 3 to 1. So number of moles of H2, this is the theoretical mass, because I'm going from the equation. If I have this number of moles, I should have 3 times the amount of moles of hydrogen. So I'm timesing my number of moles of methane by 3. I'm then looking to work out the mass. So if I've got a mass, it's the number of moles times 2, which is the MR of H2. So moles times MR, and I get 7.5 times 10 to the 7 grams. I want then to convert that into tons. So now I have theoretically the mass. Now that I've got this mass theoretically, here we go with my pen going wild. I can then take a percentage with my actual mass that I'm producing. So here I have a percentage yield 68.4 over 75 times 100. Now, if I just go back up and check, oh yes, look, they always like to do this. So many people miss that. It's got to be an answer to 3 significant figures. So do make sure that you watch for that. If you're worried about these big numbers, if you'd gone through that calculation without the big numbers, you would have come out with a similar answer. But what you'd have to really watch for is making sure that you've got the number of tons. I think if you don't put that 10 to the 6th in, you should come out with 75 anyway, which you can just put in to that reaction. So try that for yourself. If you're not confident with using these big numbers at the end, try just not using them and see if you get the same answer. I suggest you will. There is an alternative method for that where you could have worked out the number of moles of hydrogen, but I'm going to stick with the method that I've shown you there. To finish this question then, they tell you that carbon monoxide, which is produced as a waste product here in this equation, can be reacted with hydrogen to make methanol. So construct an equation for the reaction of carbon monoxide, hydrogen to make methanol. So in this case, you just put in your carbon monoxide, your hydrogen, giving your methanol, and then you'd come back and think, right, well, I've got 4 hydrogens on this side, I've got 1 carbon and 1 oxygen, so I'm balanced with the carbon monoxide, but I need 4 hydrogens. I've put in an H2, I need to double that to give my balanced equation. Then suggest 2 reasons why it's important to use carbon monoxide to make methanol. As we said before, one of them is that carbon monoxide is toxic. Whenever we get carbon monoxide in a question, that should always be a thought that you've got there. Then you've got a number of different things that you could say. It makes fuel, methanol is a fuel. Key one, I think, is it increases the atom economy, doesn't it? Because if you can find a use for that waste product carbon monoxide, because remember this is an equation here that we're looking at to produce hydrogen, but if you can find a use for that carbon monoxide, then your atom economy becomes 100%. That would be your second mark of thought there. Finally then, it's asking you a bit of a random one at the end. I mentioned it right at the start of the question. Describe how hydrogen can be used in the manufacture of margarine. So key to this is saying unsaturated oil or oils containing carbon-to-carbon bonds are reacted with a nickel catalyst, hydrogen and a nickel catalyst. That gives you your 2 marks there. So it's just simply getting you to put down what you've memorized about the process for manufacturing margarine. It's one that comes up quite regularly.